Before the workshop starts, we're going to show you how to navigate through the video. Below the YouTube video is the Show More button. Click the Show More button to reveal the index. You can skip to the point that you want in the video by clicking the blue time link.
Make a rough sketch and do it on a sheet of paper there, because I'll get you to do an accurate sketch later on to see how your rough sketch compares with your accurate sketch, okay? So there's your task. You should have that done and put that into your back pocket, that sketch into your back pocket, and we'll bring it out later. Okay, what we're dealing with this afternoon is shifting and scaling, graphical transformation of graphs. Now, I'm not really going to go into the definition, but there's the definition of the two of them. A shift is a rigid transformation that it does not change the shape or size of the graph or the function. All that a shift will do is to change the location of the graph. In other words, the graph will shift up and down, we'll say, along the y-axis. Whereas the scaling is slightly different, is a non-rigid transformation. Not really into those definitions. Students won't have to know what it is or reproduce those definitions in exams or anything like that. That's just technically what it is, shifting and scaling. But here are the various types of graphs now that we'll be looking at. Linear graphs, quadratic graphs. There's one over there at the side, it's slightly missing there, but there it is. Here's an exponential graph. There's a trig graph. There's a log graph over here at the side. There's ones here in the middle. An absolute value graph, or what's another name for that? Modular graph or modulus graph, right? That one there. They're all the type of pictures that we deal with in our mathematics syllabus, going from first year right up along, from linear right up into modular graphs right up along. And all they are pictures. And we as teachers, and later on you want the students to be able to do it as well, to put the mathematics to those pictures, or else if they have the mathematics they must be able to put the picture on them. So there's the graphs. Now I said if I saw the sunflower once more, but here's the sunflower again for you, right? Okay. Here's the sunflower, which is in workshop 4. And if we look at the sunflower, here's the graph of the sunflower. We said we went into the garden centre and we bought a sunflower which was initially on day 0 had a start height of 3 centimetres and it grew at a rate of 2 centimetres per day. Now look, graphs are great now in the junior cert and leaving cert exams and in books and so on, because you know now they're laid on a grid, and there's a grid usually in the background. So the students can actually read rise over run now for slope. And so the rise here is 2 and the run is 1, so the slope is 2. So looking for slopes is rise over run now that most teachers use and most students will use, especially when it's inlaid, when there's inlaid on a graph, on a grid there. Rise over run. This one here, the growth rate is the same. Look, rise over run is again 2. But that has a start height of 6. There's your tables. Look, first change is 2. First change here is 2, or first difference is 2. So the rate of change of growth of the sunflower, rate of change of the height of the sunflower in respect of the number of days is a constant, and it's 2. So the rate of change of a linear graph is 2. We've done that. Those two lines are parallel. Why? Same slope. Same rate of change. They will never meet. They'll never be at a time when they're the same height. They're the sort of things you talk to the students about. But here's another scenario. They both have the same start height, but they have different growth rates. We want the students to be able to, when they're at third year level, to be able to look, to be able to look at that particular line C and that particular line B, and to be able to write out the equation of it straight off. We did it in words in first year. The height equals the start height plus the number of days times the growth rate, right? You know, big mouthful there. But that's really y equals mx plus c. And c is the start height. M is the slope or the rate of change. So the equation, or how we describe that in relation to an equation, is y equals, right, 2x plus 6, isn't it? The way we describe this when we write down this in algebra is y equals 3x plus 6, because the rate of change is 3. So the students must be able to do that. Or if you give them a line y equals 3x plus 6, they should be able to make a quick sketch of it. Not make out a rake of points around, just make a quick sketch. Get a picture out there in relation to that particular graph. But now we're going to look at quadratics. Right, A, B, C, D. Now, unlike my former teacher, Lord Mason and Gus O'Brien, I'm going to go on a different rotation. A, right, B, C, you're in that group, C, D, E, F, G, A, B. All right, okay. Is that okay? Now, I want to take feedback, and the feedback I'm going to take is as follows, and we'll take feedback this way. Go back up. We're going to take feedback on C first of all. I went this way, A, B, C, right? Okay, I'll take this one, and here's C. Now I'll put it on this here again, and we'll have a look at it, and we'll talk about it in relation to this one here. Here's the C one. Now, there's the C one. And we can see on this, I can see here, there's your parent function, it's the x squared, it's the red one there in the middle, passing through 0, 0. For most of these, the parent function is x squared. That's the one you start with to compare everything else to x squared. This one here, the green one, is labelled x plus 1. And what has happened is the whole thing has shifted up one place. This one here is x plus 3. The x squared is shifted up 3 places. And this one here is x squared minus 4 is shifted down 4 places. You get a picture here of it as well. Look at it. You're dealing with x squared plus c. And this is the same effect as the line x squared plus 1, x squared plus 2, x squared plus 3, shifting up along the y-axis. The c is where the graph cuts the y-axis. And so we have it there. This one here is the x squared one. This one here is the x squared plus 1, is shifted up one place. This one here is the x squared plus 3. And this is the x squared minus 4. It is absolutely useless to students if you take that PowerPoint slide and just put it up there to them initially. They'll remember it for 2 minutes and they'll forget about it. But when they actually draw the thing themselves and see the whole effect of it moving up and down along the y-axis, that has a huge effect on them. And then you can show them the IT, right? That's the recommended way of doing it, okay? So we see the effect now of C there, and the students should see the effect once they've drawn the graphs and seen the effect of C. Okay, that's perfect. That's that one. That's called shifting of the graph up and down along the y-axis. X squared plus 1, x squared plus 4, and so on. The next feedback I'm going to take is from activity A. And G had A, hadn't she? Right, here's A. And in this one here, we have x squared, which is the blue one there. Now this time I'm dealing with a number in front. Oh, the green, thanks, the green one is x squared. Keep an eye on me, the green one is x squared. This one here is x squared, 4x squared, I'd say. That's 4x squared there, because there's 1 4 is on that graph. That one is, we started off with x squared. There's 4x squared has actually come in that way, right? This one here, blue one, is a, what was it, a half x squared? Yeah. Was it a half x squared? Yeah, half x squared. So that's actually the blue one there. When I actually put them up here, you get the picture as well. Again, recommended to get the students to actually draw it out and get the students to discuss what they're doing. There's your x squared, the red one. This is 2x squared here. This is 3x squared here. And this is a half x squared. X squared, 2x squared, 3x squared, a half x squared, wider. Right, okay? That effect, they remember that, but the arms, right, okay? And so, that's the effect of a number in front of. This, in this case, it is scaling. That's scaling now, right? Okay? So that's A. Now I'm going to take a B next. Here, they're all on the one graph. This is the x squared one here. Now, let me just put it up here. We're doing B, aren't we? Okay. And there's a number in front now of the x squared again, but this time the number that I'm going to change, I'm going to make it a negative number. And so this one here is y equals x squared, or fx equals x squared. This one here, the red one, is y equals minus x squared. Dramatic effect, it is switched upside down. Okay? And that's a huge emphasis on that. On the negative x squared graphs being that orientation switched upside down like that there. This one here is y equals minus 3x squared. It is, there's, look, x squared minus x squared, right? Minus 3x squared in closer to y-axis, right? Okay. Number less than 1 out that way again, but it's still negative. Is that okay?
You have a great game.
You could have a great. You could get them to actually. What's that graph? All right. What's this one? What's that one? Suggest what it is. Suggest what this one is. You know, right? Okay. So, all right. So there is the x squared one. Here is the minus x squared one. Here is the minus 3x squared. So you could have a great crack at them. By the way, we're going to do that. We're going to have a table quiz in a minute, right? Okay. Oh, everybody in Ireland loves a table quiz, right? Okay. I won't provide any drink at the table quiz. Okay. Right. So finger food maybe, right? Okay. Here we are. Here's the x squared one. Here's the minus x squared one upside down. There's the minus 3x squared. It gets closer to the y-axis, right? And this one here, the minus a half x squared, is further away from the y-axis. So that's that one. That is B. We had C done. That was the first one I did from C, was C. Now D is the next one. And in this one here, here's D. Here's the one we're doing. We're looking at the effect of minus x squared plus C that is up there. Minus x squared plus C. All right? And so, looking at that there, here's minus x squared is the black one. Here's minus x squared plus 1. Here's minus x squared plus 3. So we see the effect there is the same thing. When we add a number constant, it moves up and down, it shifts up and down along the y-axis. Look at it here. There's the standard x squared. Here's the minus x squared we know is that one, but this is minus x squared minus 4, it goes down. Minus x squared plus 1, it goes up 1, shifts up 1. Minus x squared plus 3 goes up that way. We're beginning to get to the stage now where we're beginning to recognize where the graphs are going to be. And so that was D. Now, the E one was as follows. The red one is x squared, which you had. That's fine, except we'll do it on the screen because of the, just to show everybody it there. There's the x squared. Now, this one here, let's do the green one there, right? This is actually, the green one is x plus 3 to be squared. That one is x plus 3 to be squared. It's anti-intuitive. Yeah. Seeing as it has gone out here to minus 3, even though the graph is x plus 3 to be squared. How do you explain this to kids? Well, I would say that if it's x plus 3 to be squared, It's like, just keep your eye on the red graph, which is the x squared, the standard parent graph. It's like taking this here, the x-axis, and dragging the x-axis out this way 3 places. Giving it 1, 2, 3 tugs. And the red graph will actually end up at the green graph. That's an Irish word, green graphing, isn't it? Okay, but the red graph will end up as the green graph. Is that okay? Actually, probably a better way of explaining it in class would be that if you have fx equals x plus 3 to be squared, all right? Along the x-axis, y is 0. So 0 equals x plus 3 to be squared, square root of both sides. X plus 3 equals 0, so that x is equal to minus 3. So the point minus 3, 0 is going to be on the graph. So minus 3, 0 has to be on the graph. So it's kind of anti-intuitive for what you're doing. So x plus 3 is actually a minimum point at minus 3, 0. Is that okay with you? So we know those type now. Look at this one here. That's x plus 1, the blue one, x plus 1 bracket to be squared. This purple one here is x, we'll say, plus 0.5 to be squared. Is that okay? That was E. Now F. Again, it's the same sort of thing, but this time, look at the graphs we're doing is x minus 1 to be squared. This one here, we have here, we'll look at this one here. It's probably clearer for you down there at the back. This graph here, tell me what it is. X minus 3 squared. Tell me what the blue one is. X minus 1 squared. Bracket. Inside in the bracket is x minus 1 squared. That one there, a half, x minus a half squared, and that's the x squared. It's like, again, dragging your x-axis, we'll say for the green one there, 3 places here in the positive direction. Is that okay? And so therefore we end up with, three places in the negative direction out this way. We're dragging 3 places in the negative direction. So we end up with x minus 3, right? Or x plus 3 to be squared. That's where the graph ends up. Is that okay? Now that was F. And finally G. Gx equals ax plus c. Now here's x squared. Let's do it in steps. What's that one? X plus 1 bracket squared, isn't it? Yeah. That's x plus 1 bracket squared. As we said here, now that one is x plus 1 squared plus 2. It's gone up 2 places, hasn't it? Is that okay with you? Yeah. So you see the effect there. You do one thing, move it either that way or that way, and then up the way, or else down the way. Okay? And so there's G. Look at this one here. There's x squared. There's x plus 1 squared minus 2. Right? There's x squared. And this one here is x squared plus 1 minus 2. Table quiz. Table quiz. On the activity there, on the book there, on page, I can't see now, page 35, I'm going to flash these functions up on the screen and I'm going to get you to write them down. Different forms of quadratic functions. Now, we're used to seeing quadratic functions like that. Yeah. The one I put up this morning was x squared minus x minus 6, my favourite one. Like they ask, what's your favourite function? My favourite function is x squared minus x minus 6, right? But these functions here, that's the standard form of a quadratic. That's the same quadratic. That's called a factored form of a quadratic. And this one here is called a squared form of a quadratic. We are not used to working with this. Now, if you look at those 3 forms, and we're talking about now going the opposite direction looking at the function itself and trying to get the picture from it. There we were looking at the picture, the table quiz thing, and we were writing down the functions. Now we're going to look at the functions and look at try and sketch the graph. That's brilliant. That first one is brilliant for me, no problem. I can use that hugely. C is 5. In other words, there was a nice marker I had. In other words, it cuts the x-axis 1, 2, 3, 4, and 5. Or what cuts the y-axis? We can tell straight away from the first form the intercept is -5. Hey, I have a point on it already. The second one is brilliant as well, because it's a factored form. We can get the roots, 5 and -1. Is that okay? 1, 2, 3, 4, 5, and here's -1. You know, if you let that equal to 0, you'll get x equals 5 and x equals -1. This format is brilliant, the last format. Absolutely brilliant. It's very easy. Get from there to there, isn't it? Mm-hmm. Factorize. It's very easy get from there to there, isn't it? Mm-hmm. It's easy get from there to there by multiplying out. Mm-hmm. But here's the difficult bit. How do we get from here to here? Complete the square. Now, completing the square has not been mentioned at junior. It's not on junior cert level, but it's a very handy thing to have in your armory when you're dealing with junior cert quadratic graphs. So that if we take x squared minus 4x minus 5, how do we complete the square on that? In other words, get it from that form to that form there. And we complete the square no problem, because we take half of that and we get 2, and then we square it. So 2 squared is 4. So we go x squared minus 4x plus 4. I'm after adding in a 4 here, so I'll have to take it away again and then minus 5. Is that okay? I'm after adding in a plus 4, and I'm here to get the plus 4, half that and square it, add it in and take it away.
And is it always half the middle?
Always half the coefficient of x, always, all right? So we now take x squared minus 4x plus 4, and we group that together, minus 9. Is that okay? Mm-hmm. We can factorize this bit here, and we get x and 2 and 2, and they're both minuses. Minus 9, and so we have x minus 2 to be squared minus 9. Hey presto, from that form to that form. We can now sketch that brilliantly. We know from what we've been doing just previously, x minus 2 is out this way, isn't it? And then down 9 places. So x minus 2 and then down 9 places, 5, 6, 7, 8 and 9, and so we know that's the minimum point of the graph. The minimum point of the graph is 2 minus 9. That's what's so beautiful about the squared format, is that we can read off either the minimum or the maximum of the graph straight off. And look, we now have a lovely number of points there, so we can go around. And there's our quadratic graph. Is that okay? Just shove that up there a bit, right? Okay? Right. We are not used to dealing with the squared format, but the squared format is absolutely brilliant. There's the graph there. Try that one. Have a go at that one. All right? Junior Cert higher level sample paper. Strand 5 and phase 3, you know all these phases. Your present junior certs will not be doing this. Your present second years, yes. That's the way the context to put it in. So next year, for your third years who are doing it, doing the junior cert in 2015, this is fierce relevant. No longer will they ask, or did they ask, draw the graph of x squared minus x minus 6 in the domain minus 3 plus 3. Two graphs, fx is that. Now look at the format it's in. X plus 2 to be squared minus 4, x minus 3 to be squared as gx. you're asked, match the graphs to the functions by putting fx and gx in the corresponding boxes. In other words, which is this one and which is this one? Well, we know now from the work we did. Minimum value is -2, -4, isn't it? -2, -4, so that particular graph must be fx, isn't it? This one here, x plus 3 minus 4 is the minimum value. There is nothing stopping students of looking at those two functions there, multiplying it out, factorizing, finding where it cuts the x-axis, and the same thing, but it's way longer. It's way longer. It's far more understanding when they write it in squared format. They don't have to. It's not on the syllabus, but it's just a help. Write down the roots of the two functions. Previous to this, we would have got that, and that it said factorize and find the roots or solve the equation. Now all they have to do is go to the graphs and read off where they cut the x-axis, because that's asking for understanding. Do they know what roots are? Do they know what the picture means when the roots means it cuts the x-axis in two places? Where does it actually cut? The roots of fx are -4 and -1, and the roots of this one, gx, are 1 and 1 and 5. Next part of sketch. Sketch the graph of that. Minimum value is, they could multiply it out, draw the graph, or sketch the graph from that. But look, minimum point is 1 minus 4. So 1 minus 4 is here, have the minimum point in the same shape of graph. It's a sketch, it's not a diagram, it's not a graph, it's a sketch, so they just sketch it. Are you okay with that so far? Mm-hmm. Now, part D. That thing there, x minus h to be squared minus 2 equals x squared minus 10x plus 23. H is an element of n. Find the value of h. Natural number, right? H is a natural number. Oh. I'll write it here. X minus h to be squared minus 2 equals x squared minus 10x plus 23. I could work from this side to this side. If I do that, or I could work from that side to that side. Let's do from this side to this side first. Complete the square. Half that we get 5, square root 25. So it's x squared minus 10x plus 25 minus 25 plus 23. Is that okay with everybody? Mm-hmm. Factorize those first three bits and we get x minus 5 all to be squared, and then that is minus 2. X minus h to be squared, so h is 5, isn't it? H equals 5. Or you could work the other way. You could work this out. Square the first, square the second, twice the first by the second. That's the thing I do when I'm teaching. I talk out loud an awful lot. When you talk out loud a lot, and when you're talking your thoughts going through a problem, you're actually teaching the kids your train of thought that's going on in there in your head, and it's helping them with your problem solving. They begin to talk to themselves as well. Am I going right here or am I going wrong? That sort of questions, you know. Or will I go this way or will I go that way? What's the advantage of going this way? What's the advantage of going that way? That's the sort of conversation I have with myself when I'm at the board doing a problem, but it's a conversation that the kids hear because I speak my thoughts out loud. There's no problem in giving the kids little mnemonics to remember. Square the first, square the second, twice the first by the second, right? Cube the first, cube the second, 3 times the first by the second squared, 3 times the second by the first squared. You know those ones? Yeah. They'll always remember those things, right? Okay? Right? They might remember what it's applicable to, but they'll remember them. So we've squared that, and then there's a minus 2 there, and that was equal to x squared minus 10x plus 23. All we have to do now is compare the x bits. There's an x bit there and there's an x bit there. And so minus 2xh is equal to 10x, so therefore minus 2h will equal to minus 10, and so h will equal to 5. Same solution, h is 5 and h is 5. The easier way to do it was completing the square, but you didn't have to do it that way. Right? So completing the square is not on junior cert level, even though it's a fierce handy thing to have. Okay, write the equation of the axis of symmetry of this particular graph. Well, once I have h it's no problem now drawing the graph of that, because when I draw the graph of that, no problem drawing the graph of it if I can find it here, this one here, back here, one more, no still, back here, yeah, found a page. Right, if I draw the graph of that, we know that h is 5, and so therefore it's x minus 5, so it's 5 minus 2 are the minimum value, isn't it? 1, 2, 3, 4, 5. 5 minus 2 is there, and there's 5 minus 2. And we know it's a positive x squared graph, so it goes that way, isn't it? And so the axis of symmetry now is simple to do. The axis of symmetry is this one here, and the axis of symmetry is x equals 5. And there's all the question done. That's the type of question that's been asked in the exam. That's the type of question, that was the question that came up in the sample paper. It's a different sort of question on quadratics. It tests more understanding than anything else. Okay? And I would say it is a step for teachers to take to get away from draw the graph of, but they still need to be able to draw the graph of and make out points and be able to put, there's far more understanding and all of that stuff there. A lot of countries call it pre-calculus. We don't in this country, but that's pre-calculus. Because we're getting them to draw graphs quickly, so that if they're asked for integrals at higher level maths, they'll be able to quickly draw a sketch of a quadratic. They'll be able to locate where the area they're looking for in the integral is. And that's that stuff. So, for what it's worth, that's that question. Now, another activity, and this is the last activity of the day. You'll be glad to hear. I know everybody is getting tired, but there we go. I'm just handing out this. This is a graph matching activity, and we'll do it table by table. Okay, I think most people are there. And as I said, that's up on the website, and it's a really good matching exercise where they're matching different forms of the quadratic. And I see you're all looking up now behind, because I've taken a photograph of the solutions, right, that people had. And these are the second, but I think these are the second ones. If I go down here, they're the top ones maybe. They're the top ones there, I think. I don't know, you can match them up. There's my photography skills aren't very good. I'd need to hone those in a bit. But it is an idea that if you wanted the feedback and if you wanted the answers, take a photograph of the stuff there. Just before I move away from the iPad stuff, I really should show you, and I meant to show you early on, was that there is this app here. It's called Sketchometry. And here it is, look.
Start a new one there for us to have a look.
I'm starting a new one. There's a new one. Hey. On my iPad. If I want to draw a point on the circle, there's a point on the circle. If I want to draw the radius of the circle, all I do is that. If I wanted to draw a tangent to the circle, all I do is draw a perpendicular line here. Or even go that way. Or even go that way. All right, close enough. All right, I can actually move this in. If I actually drag this in, I can actually move that in there. Now we know, and we can measure. And by the way, you can also do functions on this. And so therefore I'm going to look here more, and I'm going to look at fx. There's functions on it, and it brings up a keyboard there. You can type in your functions, like if you wanted fx equals, we'll say e to the x. You can just type it in here. We'll say e to the x, or we'll say exponential e to the x. And hit, I think, again, I wouldn't be, I'd do maybe that. And there it is there, look, you can see it there in the background, e to the x there in the background, do you see it? It's that line there, do you see it there? Right down there. That's the e to the x. So you can do your geometry, your functions on it. It's very, very easy to use. Very easy to use. The only other thing is GeoGebra, as well as on the iPad now. You can do all the geometry stuff. It has all the same icons on it as in standard GeoGebra. You can see it there. And there's your graph. So therefore, here's your input bar down there, so that when you want to type in, we'll say f bracket x, f bracket x, close your brackets again, equals, and we'll say here's the equal sign in here, equals, we'll say 2 to the x, we'll do 2 to the x, there's 2, and we'll do to the power of, here's the power of, where's 2 to the power of is up here, 2 to the power of x, and so hit return, or hit enter, and there's 2 to the x there. Just drag that across, and there's your graph of 2 to the x, right? On GeoGebra on your iPad. Again, it's far more accessible to students and so on when it's wireless. When you can walk down around the room and hand it to a student, get them to type in 2 to the x, they can actually draw the graph and so on. So that's just, I just wanted to show you those before, I mentioned them earlier. Just wanted to show you before we finish today. The only other thing is any of these particular ones here that we had on that, the graph matching exercise there, that we had, here was the solutions to them. There's all the solutions to them if you wanted to see them. I know you've them all put away now back into the bags and everything again, but the solutions as well are up on the website, right? Okay. By the way, last one or two. There's a summary, and using GeoGebra to do a lot of this stuff as well. You could do a lot of this stuff as well on GeoGebra. The same holds for cubics. There's shifting and scaling in cubics as well. And so therefore there's a cubic. If we had, instead of having 3 here at the end, if we had 4 or something, the cubic will shift up the way. So the same thing hold for shifting and scaling there. Do you see that one here? Instead of the x, I'm replacing it by x plus 6. Okay? And again, that is anti-intuitive as well, because look where it's going. It's going 6 places in the negative direction. And the same with that one there. There's another one. That is putting a number in front of all of the cubic function. It squashes it down. And again, here's one which is a standard modulus graph, or what do I call them? What was the other one? I call them a modular graph anyway. Modulus, graph of a modulus. Some people call them graphs of absolute value. But look, same thing. Modulus of x plus 4 shifts up 4 places. The other thing, do you see this one here? That is x plus modulus x plus 4. See that? Same things. Once you've done a junior cert in relation to cubics, you have it done then for leaving cert. You've all the groundwork laid in relation to all of that. And again, there is 4. Look at it, it's like, whoosh. Again, narrower, right? Again, there's a combination of 2, x minus 3 plus 4, the absolute value. Sin x, these graphs are on for leaving cert, and cos x graphs. Putting a number in front, a sine 3x. You know these ones? All of those can be done in relation to shifting and scaling. That one is sine of x plus 4. Okay? All of those, you can detail them there. That sine of x plus pi, it's a phase shift to pi over 2, moves over that way. And again, the range has changed from, the initial range was +1 to -1, now it's +5 to -5, because there's simply a number in front. And so they have the same with the log graphs, as we say, shifting up and down. Very same thing, and try to relate them back to the quadratic. Okay? And I think basically that's most of the stuff that I had there in relation to all of that. And I think that's us finished for the day. All right? And thanks for your attention. I hope you enjoyed the day.